Okay, so welcome back. So I think we will just, I didn't erase the board, normally I do, because I think it's good to have a recap. So we explored row operations, elementary row operations last time. And what else did we explore? Let's see. Some examples, linear equations. And then we set up this notion of a row reduced echelon form. In fact, we saw some examples of solving linear equations where inevitably the idea was to reduce a given linear system, an augmented matrix A and B, to a row reduced echelon form for A. And then you can read off the solutions. Okay. So let's formalize this. Just to remind you, this was from last time. A matrix over an arbitrary field of an arbitrary size is in row reduced echelon form if all the zero rows are below all the non-zero rows. So like here, all the zero rows are below the non-zero rows. The leftmost non-zero entry in any row is 1. So, right, so 1 and then no other entries. In any column containing a leading 1, all other entries are 0. So, if you look at these ones, the leftmost non-zero entries, look at the column containing those entries. Every other entry is 0. Okay? And the fourth one is also important. The leading ones occur from left to right, which is not satisfied by this. So, the last condition is violated. So, this matrix is not in row reduced echelon form. But things like the identity matrix patterned by zeros like this is in row reduced echelon form. And then we come to the main theorem of solving linear equations. Fix a field F and of course integers of a given size and an augmented matrix. So either a matrix or an augmented matrix. Then such a matrix A can be transformed to a matrix A prime in row reduced echelon form by a finite sequence of elementary row operations. That is part 1. Part 2 says that this matrix is unique. Okay, so part 1 is going to be sort of the easier half, the existence part. The uniqueness is not too hard, but it has some subtlety involved. Okay, so we will get to that. So now the rest of the class, today's class, I want to prove this statement and mention one application. And so the goal is that the hope is by the end of today's class, we will finish with linear equations and this theorem. Next class, I want to start with, if I can get there, vector spaces, basis, dimension, linear independence, and so on. Okay, so let us begin by trying to prove this statement. And as an application, I will tell you. So I will prove basically a couple of corollaries, but the main corollary of this theorem is that a matrix over any field is invertible if and only if it is square. I mean, so if it is invertible, then it is square. And I will give you a bunch of different criteria for if a matrix is invertible, if and only if 3 or 4 other different conditions. And in particular, it will be square. Okay. So we have already used the trace to prove that statement over a field of characteristic 0. But this proof using this row reduced echelon form will go through for any field of any characteristic. Right? So that will give us a second proof for characteristic 0, but in fact a more general argument because it works for every field. Okay. So let us start by so before we actually get to this theorem, I want to make a little bit of digression and mention some other things. So basically row equivalence. Okay. So definition: two matrices are row equivalent. So two matrices are row equivalent if you can get from one to the other by a finite sequence of elementary row operations. If one, or if there exists a finite sequence, if there exists a finite sequence of elementary row operations, It's visible. Yeah. Operations sending A to B. Okay. I'm just saying sending one to the other. But I'm saying that they are row equivalent. So somehow equivalent should tell you that this is an equivalence relation. So which means that we will say that right now. Right? So and the point is that's obvious because if you can send A to B by first swap two rows, then rescale some row. Well, then you can send B to A by first unrescaling that row and then unswapping those two rows. So carry out the reverse operations in the reverse order, right? So the idea is because every elementary row operation is reversible, you carry out the reverse sequence in the reverse order, you get from B to A. So that's what we will do, in fact. And so there are two, I guess I should call this a lemma. There are two conditions. First, row equivalence is an equivalence relation. Equivalence relation on the set of matrices of any given size for all n. And the second is if A and B are indeed row equivalent, then they have the same set of solutions. Okay. So yeah. Are row equivalent, then AX equals 0, I guess, whatever. Sorry. Are row equivalent augmented matrices. Okay. So I'm even giving you the A and the B. AX equals B. Then they have the same sets of solutions. So start with the linear system AX equals little a. Change a few, do a few row operations, get to a linear system Bx equals little b. Then these two have the same sets of solutions. So if A, B are row equivalent augmented matrices, then they have the same sets of solutions. That's what it says. Okay. So we'll get, I won't write this theorem down again. Or maybe I will, let's see. But first I need to tell you this lemma. This is sort of formalizing some things that we said last time. Okay, so do we prove this right now or yeah? Let's prove this. So proof. So first part one. Okay, A is obtained from itself. So you have to prove three things, right? Equivalence means reflexive, symmetric, transitive. Is A row equivalent to itself? Yes, by carrying out no operation, or by rescaling one row by one, or by swapping two rows and swapping them back. So that's clear. So A is equivalent to A. So maybe I should have said firstly write A tilde B if A is row equivalent to B. Write A tilde B if A is row equivalent to B. Well, see here. This should be what goes. Clearly, A is row equivalent to B. Okay. What about symmetry? Well, that's again obvious. Maybe I'll write this down formally. Okay, so you should see how proofs are written formally. Symmetry. So this is point number one. Point number two. Say A is row equivalent to B. What does that mean? It means that implies B is something like you start from A, you apply E, maybe E1 or E2 or E3. Let's call it EA1. So A1 can be 1, 2, 3 with some parameters applied to A. Then you apply EA2 with some parameters to A, to E1 of A, and so on till you get to E, I don't know. So what do we call it? K, EAK. Some parameters applied to, right? Where each AI is belonging to the set 1, 2, and 3. What does that mean? It means that these things are elementary row operations of the first kind, second kind, or third. Okay? But then now the point is each of these row operations is reversible since each elementary row operation is reversible and the reverse is also an elementary row operation. Actually, in fact, even better. Since the class of elementary row operations are closed under inversion. Since the set of all elementary row operations on F to the n by n is closed under taking inverses, so you start applying the inverse. So first you take EAK star, the inverse of this is again EAK star, and so on and so forth. So you get, so I will say this, I'll say A equals, so first you take B, you apply this outsidemost element EAK star inverse, apply to B. Then you take the next one, you take E, A, K minus 1 star inverse applied to this and keep going. And finally you do E, A1 star inverse applied to E, A2 star inverse applied to so on. Right? So you take all these row operations, but each of these inverses is also a row operation. If this is E3 of something, then the inverse is also E3 of something. If this was E2 of something, then its inverse is also E2. So every one of these is still an elementary row operation. And so you get to the matrix A by applying finitely many elementary row operations from B, and so B implies. So B is, if A is row equivalent to B, then B is also row equivalent to B. Okay, and then the third one I will probably give to you as an exercise, but basically you have EA1 star, EA2 star, EAK star, and then you have EB1 star, EB2 star, EBL star. Well, so if you apply the EBLs to B, that means you're applying the EBLs to this, all of these to A. That's still a finitely many. So I'll leave it to you guys to check transitivity for yourself. But I'll just maybe write it down very, very. Okay, so this is the second one, and then the transitivity. Say A is row equivalent to B, and B is row equivalent to C. So that means that there exist these. So B equals something like this: E A K star, E A2 star, E A1 star A, and C equals E B L star, let's say, E B2 star, E B1 star of B. But then just plug in this expression for B over here and you're done, right? So this is just easy. C equals EBL star double dot EB1 star applied to EAK star double dot EA1 star, everything of this applied to it. And so indeed there are finitely many operations taking A to B to C. So taking A to C. Okay, so this is part 1. Part 2, if these are row equivalent, then they have the same set of solutions. I think that we already saw. Right? I mean, maybe I can augment it, right? So let's just say that. Okay, I'll write it down completely formally and explicitly, but basically part 2 says the following. So first the claim. Say some elementary matrix E, A, A1 star of, let's say, A prime A, this is my matrix A, equals B prime B. Then the solution set of AX equals A is equal to the solution set of BX equals B. A prime X equals A. Actually, I'll say even better, are contained in B prime X equals B. Sorry, are not contained, are solutions of. So the solution set of these are also solutions of these. This system. And therefore the set of solutions is contained. The proof of this is trivial. The point is every elementary row operation is equal to this applied to the identity matrix multiplied by that, right? So let's say AX equals A prime X equals A is now capital A is the augmented matrix, which is A prime and A. Then if I multiply by this, okay, and let A and define the elementary matrix M to be this thing applied to the identity E A star of identity matrix. Identity M cross M. Then what we know from last class, from last week, and from earlier, from class, or from homework, I forget. I think from class. Sorry, not yet from class. So because AX equals A prime X equals A and M is defined this way, yeah, so what do we get? The same number of rows, yeah, and the same number of columns. So what we get is M times AX, A prime X, equals M times A. Right? But this exactly is the solution. This means that X is a solution of this augmented matrix. X is a solution of what? X is a solution of this augmented matrix M A prime M A. But now this is where we use the theory of partition matrices. As I told you, this is exactly equal to M times A prime A. And what was M? M was exactly this. So this is equal to E star A identity times sort of A prime and A. But applying E star of identity to any matrix is like applying E star to that matrix. That is it. So this is the part that was from class. And that is precisely B prime and B, that's the definition. So if X is a solution of AX equals A, let's say X naught is a solution of AX equals A, then X naught is also a solution of B prime X equals B. And now basically the claim is proved and therefore we are done. Why are we done? So this proves the claim. So first of all, this shows the claim, right? That the solution sets are contained. But now, what was the question? The question was, if you have two matrices which are row equivalent, then their solutions are contained, their solution sets are equal. Well, because of this we can say, so by the claim, if this is the claim for a single set, if you apply a single matrix, So maybe I should say apply the claim inductively, right? So if one matrix, one elementary transformation changes A to B, then you're good. Then the solution set is contained. So if two elementary transformations change A to B, then the solution set after two operations is contained in the solution set after one operation. Sorry, the solution set after zero operations is contained in the solution set after one, is contained in the solution set after two. It's like saying if A prime x equals A, then M1 A prime x equals M1A, and then M2 M1 A prime x equals M2 M1. And so two operations, and three operations, and four operations. And so inductively, applying this inductively, or repeatedly, shows that if A is rho equivalent to B, then the solution sets of A are contained in the solution sets of B. By that principle. The solution set, then the by A, I mean, remember, A is an augmented matrix of this kind. So the solution set of A prime x equals A is contained in the solution set of B, meaning again B prime x equals B. And now here is where I use part 1. The point is, rho equivalence is an equivalence relation. So if A is rho equivalent to B, then B is also rho equivalent to A. In particular, the solution set of B is contained in the solution set of A. And so we have containment both ways, and therefore they are equal. Okay, so that's how we proceed. Since this tilde is symmetric, the reverse inclusion holds as well. And therefore we are done. So this we also obtain the reverse. We obtain the reverse inclusion. This reverse inclusion as well. Okay, so that's how we prove that the solution sets are the same. Okay, so now what do I want to do next? So now that we have proved these two facts, now let me remind you again of that same theorem about rho reduced echelon forms. So theorem. Okay. So I'll just state it slightly differently. So given the field and with integers m and n bigger equals 1, and the matrix A in F to the m cross n. Then given these data, A is rho equivalent, so in this language, A is rho equivalent to a unique matrix in rho reduced echelon form. To a unique matrix in rho reduced echelon form. That is the statement of the theorem. Again, and of course, if A is augmented, then this unique matrix is also augmented. So that's okay. Let's try some other black pens now. So maybe I'll show you. Let's see, how do I do this? I will do this by just showing you some algorithms. Let me apply this to a matrix here. So I'll do an example here, and I will write down the proof. So let's start with the matrix. Okay, so let's start with the matrix. This is an example. A equals 0, 0, 0, 1, 0, 2, 4, 2, 0, 3, 5, 1. Okay, I'm going to start with this matrix just as an example. Okay, and so here I'm going to call this matrix M0, and then I'm going to set K0 an integer to be 0. So at every stage, I'm going to keep track of M0 and K0, the matrix M0, integer K0. From there, we will get to a matrix M1 and an integer K1 of the same size, then M2 and K2 and so on. So the idea is the following. Fine. So let's start looking at it from the leftmost column. Well, every entry is 0. So then I move on. Now I look at this column. Here is a non-zero entry. Look at the topmost non-zero entry. Okay. Now what I want to do is, first of all, I will apply the operations E1, E2, and E3 exactly once. So E1 is to rescale, right? This is non-zero. This is in a field. So therefore, you can divide and make this 1. Okay. So over here, I'm assuming I guess the field has characteristic not 2. So 2 is not 0. Okay. So I'm going to apply E1 now. And you can figure out E1 of the second row divided by 2 or multiply by 2 inverse. So I get 0, 0, 0, 1, 0, 1, 2, 1, 0, 3, 5, 1. Okay, I'm going to apply the first row operation. The next I apply the second row operation. This row must be moved to the top as high as I can. So I'll go 0, 1, 2, 1, 0, 0, 0, 1, 0, 3, 5, 1. Okay, this is E2. And then finally, I will make all the entries below in the same column, below this leading 1, 0. So now I apply E3. If it was a non-zero entry here, I would have made this 0 as well. And so on. So after I do E3, I get 0, 1. So the first row doesn't change. The second row doesn't change. The third row, this becomes 0. That's the whole point. 5 minus 3 times 2 is negative 1. And then 1 minus 3 times 2 is negative 2. Okay. So we got, maybe I should really squeeze this a little better. So first I do 0, 0, 0, 1, 0, sorry, oops. 0.0121, 0, 0, 0, 1, 0, 3, 5, 1. Now I get 0, 1, 2, 1, 0, 0, 0, 1, 0, 0, negative 1, negative 2. This is E3. Okay, so this is my third row operation. So that's how you keep doing row operations. And now I'm going to write the same thing down formally. Okay, so proof of existence. This is part 1 of the theorem I ended last time with. It is the same theorem. Okay, so set K0 equals 0 and M0 equals A. Now do the following. Now, so this is still now given K, J bigger, sorry, let's even say this. Let's make a, remember that A is an F to the M cross M. Okay. So now I'm going to give, as basically the KJs mark the positions of the pivot ones or the pivot columns. So KJs must be less equals N. So given 0, less equals KJ, less equals N for some J. And MJ, so given this and MJ belongs to F to the M cross M. This is the data we are given, right? An integer Kj and a matrix Mj. So given this thing, do the following 3 operations. Okay. So so we will do a sequence of row operations. We will perform. I'll just say do. we will perform a sequence of row operations to get to kj plus 1, strictly bigger than kj, and mj plus 1, a matrix, as follows. So here are the row operations. So the first row operation, as I said, is E1. Find the topmost row. So okay, choose the smallest kj plus 1. Choose the smallest such that what happens? So by the way, with M0, I didn't care about the first row. But now after this, I will care that the first row is exactly this, the leading one is this, and this row is locked. Meaning beyond this point, because all the other columns are 0 here, I will never bring anything up to the first row. The first row is locked. Then I will look at the entries here and say, look, well, this is the next. The first column is done, the second column is now done. So I look at the third column, except this first row. Look, here it is. Here is an entry which is non-zero. Push this up, rescale to make it 1, and then kill off everything, even including this entry. Okay, so we will keep doing that. So, but then we will never push it up to the first row, we will push this up to the second row. That's the point. We will not push it up to the first row. So, choose the smallest kj plus 1 bigger than kj. Yeah, such that there exists a row below the first j rows. Such that there exists a row in mj. I mean, keep doing this until you don't find such a row. Right? So there exists a row in mj below the first j rows. It's a non-zero entry in the kj plus first column. With a non-zero entry in the kj plus first column. Okay? This is the first step. The second step is to rescale that entry to make it 1. So, okay, sorry, I should have said that. This is all E1. Okay? So, rescale this row to make this entry 1. That is E1. Then E2 and E3 are to swap. So maybe I want to continue this calculation example here. So maybe I'll put it. Step 2 is to swap. Swap that row with the j plus first row. The first j rows are no longer to be touched. This row is no longer to be touched now. So swap it with the j plus first row. That is the second step. This is the E1. E2 is exchange this rescaled row and j plus first row. Of the matrix. That is E2 because E2 involves exchanging rows. E3 is to now use that entry, that non-zero, the 1 entry. Now the 1 entry is now a leading 1, right? So use this leading 1. So perform E3 operations, row operations, the elementary row operations of the third kind, using the leading 1 in the j plus 4. Now that row is the j plus first row. To make all other entries, we in fact know which column it is, right? It's in the kj plus first column. That's where the non-zero entry occurred. Leftmost, that's the one we made 0. We made 1. So to make all other entries 0 in that column. To make all other entries equal to 0. Okay, so that's exactly what we did. E1, E2, E3. Just that we did. Now let's do the same thing and then repeat. Repeat these steps. Sorry. So now I should tell you that the matrix we get, so we already got the kj plus 1. Call this resulting matrix mj plus 1. Resulting matrix mj plus 1. So now given starting from a matrix mj and an integer kj, we did a sequence of row operations to get to kj plus 1 and mj plus 1. Okay, so that was what we did. Great, let's do that here now. So we have already seen what happens here. Let's now again do the same thing here. So E1 now for this one, you see. I look at the first two columns are done. I look at the third column after the first two. That row is fixed. Aha, there is a non-zero entry. Make it 1. So 0, 1, 2, 1, 0, 0, 0, 1, 0, 0, 1, 2. Okay, now after that, this row should be pushed up as much as possible. You are no longer allowed to touch the first row because j equals 1 now. So you take it to j plus first row. 0, 1, 2, 1, 0, 0, 1, 2, 0, 0, 0, 1. This is after union T2. And finally, now you see, let's look at so this was a leading one. This is now a leading one. Because that's what we did. We rescaled it and then we pushed it up. And now this entry is a leading one, so you must use it to kill everything in the same column to get to row reduced echelon form. So let's kill it. So now this needs 3, 0, 1, and now this 2 becomes a 0. And from 1 I subtract 4, so I get minus 3, 0, 0, 1, 2, 0, 0, 0, 1. Okay. So now this is my matrix. So let's see. So M0 was this, K0 was this. Here now, K1 is 2. Is the second column, so K1 is 2. And this matrix is M1. Now over here, now the first column is done, the second column is done. This is K1. The second leading one occurs in the third column, so K2 is 3. And this matrix is M2. This matrix, so M1 here, M2 here. And then finally, the last thing you again do is the same. So you identify, okay, the first 3 columns are now gone. Look beyond that. Choose the smallest column bigger than K2. Well, there is only one more column. And indeed, it has a non-zero entry. So my K3 is 4. And then from this, I don't need to swap anything. This is already where it should be. But now I need to kill these 2 entries. And so do E3 twice. 1 E3, followed by another E3. And the point is, these 3 entries never get touched. These just become 0. And so we have exactly 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And guess what? This matrix is exactly in row reduced echelon form. So my K3 is 4. Is this leading one? The column number. And of course, this matrix is M3. Okay. And you stop here. So keep doing this until you can go no further because you stop. So what happens at the end? It's pretty much easy to see that what we did from all these things was because we chose the leftmost column that worked. The leftmost column that worked, the smallest kj percent bigger than kj. Therefore, we were really taking the leftmost one, the leftmost non-zero entry and making it 1. And then we pushed it all the way up. So all the 0 rows come down. Then take the next row which is non-zero, push it up, well, in the leftmost column, push it above again, use it to make a leading 1 and kill everything in the column. So we are literally doing the steps to get to the row reduced echelon form. And so I won't even say anything here. Repeating, or let's say, inductively repeating this. Inductively repeating this procedure, we eventually obtain, when we can go no further, a matrix in row reduced echelon form. So that part is the easy part, we just keep doing this. a matrix in row reduced echelon form. Okay, so that's the first part. That's the existence part. The uniqueness part is slightly trickier. Let's get there now. Okay, so this is why its existence is true. And now let's look at uniqueness. Maybe I should ask an example first before doing the uniqueness part. Let's see if we can discuss an example. Okay, so this is part one. Uniqueness. That's the question, we want to prove it. Why is the row reduced echelon form unique? Okay, we are about halfway through the class, I guess. So that there is a key thing. Okay. Suppose, okay, let's take an example. So before I prove uniqueness, let's look at an example. That is the pen there. So first, let's look at some example where we say start with the matrix AX equals A times U equals 0, where U is a vector, A is a matrix in row reduced echelon form. So say, this is a bad pen. Maybe okay, this I should use blue pen. A is in row reduced echelon form, and A times U equals 0. Okay, so this is a vector, that's a vector. So let's look at this. So let's suppose, for example, I have a 1 0 0 0 0 1 0 0. Okay. Sorry, I should have said something. So A is the row reduced echelon form is such that if AU equals 0, so every solution of AU equals 0, okay. Oops, I should also have said the size of the matrix. This is M cross N. And so this is N cross 1. U is a vector of N coordinates. If AU equals 0, then UN equals 0. The last coordinate of U is 0. Suppose this is true. What can you say about the last column of A? Sorry, one second. Okay, so what can you say about the last column of last column? What can we say about that? Okay, so I'm not writing that fully. Okay, so let's see. So let's do an example. So suppose, can I have this times U1, U2, U3, sorry, U4. Okay, suppose this is equal to 0. Suppose I have this thing where the last column is 0. Does this have to imply that UN U4 equals 0? Let's check. What we get is, we would get U1, U2, U3. And the last, sorry, something is wrong. You get U1, U2, U3. And this has to, so this is 0. So this means that U1 is 0, U2 is 0, and U3 is 0. But it does not imply that U4 is 0. Right? If this is 0, then U1 equals U2 equals U3 equals 0. But it does not imply that U4 is 0. 1 second. So need not be 0. So this is what we don't want. So in particular, that's the problem. So unless the last, so how can we guarantee that UN must be 0? Well, if the last column does not contain the leading 1, then there is no guarantee of that. So check for yourselves maybe. So check for yourselves that basically the idea is the following. Okay, I think I said something about free variables last time. So if the last column does not contain a pivot one, if the last column is not a pivot column, then it doesn't correspond to a pivot variable. The point is pivot variables are the variables that are fixed, that are uniquely determined. The remaining columns, the remaining variables are free variables, and so they are allowed to take any value in a row reduced echelon form like A U equals 0 kind of thing. So and that's the reason why if this happens, then the last column of A must contain a leading one. Let's call this star. This condition here. Let's call this condition star. If star happens, if star holds, then the last column of this row reduced echelon form contains a pivot, contains a leading one. Leading meaning leftmost. Entry 1, which I'm putting in the box. Okay. So that's just I have not yet started proving the uniqueness. I'm just writing down some observation about this thing. Now let me start proving uniqueness. Maybe why not on that board itself. Okay, so maybe I'll start here. I need a pen. Proof of uniqueness. Okay, so proof of uniqueness. This is going to be by induction on the number of columns, which was n. Remember, my matrix was m cross n. It has n rows and n columns. So we are going to prove this by induction on number of columns. Let's start with n equals 1. What does this mean? It means you have a row reduced echelon form. You have a matrix with one column, and however many rows you want and one column. Okay, so either that matrix, and let's say this matrix is in row reduced echelon form, right? So either the matrix is all 0 entries, that's fine, or the matrix has at least one non-zero entry. But then first of all, if it has the one non-zero entry, that must be a leading one. That entry must be 1, and then all other entries above and below must be 0. That means the entire row becomes 0. So how can a 0 row be above a non-zero row? In a row reduced echelon form, all zeros are below. So only two matrices in row reduced echelon form are the all zeros column, or the one here and all zeros below. So this one, I'll just say that, and again I won't write it down. It's obvious from the definitions. The only column matrices or column vectors are the zero matrix n1 cross n. Sorry, n cross 1, m cross 1, m rows and 1 column, and uh, 1 0 dot 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 0. This is also called E1, but we will see this later on. The vector E1 is the standard basis vector. Anyway, we will see this later. So these are the only two, and clearly these are not row equivalent to each other, right? Because one is the zero matrix and one is the non-zero. These are not row equivalent to each other. These are not row equivalent, so therefore these. I'll just say not row equivalent. If anything, you can ask what matrices are row equivalent to a zero matrix. And the answer is no matter what row operations you do, starting from a zero matrix, you will always get only the zero matrix. So if you have this matrix, it cannot be row equivalent to anything that's non-zero. And that's the equivalence relation. So these are not row equivalent. Therefore, this is obvious, right? So if you have any matrix which one column which is row equivalent to something in RREF, it has to be row equivalent to either this one or that one, and it cannot be equivalent to both because they are not equivalent to each other. So the result is obvious. So now the induction step, this is the base case, and then there's the induction step. And of course, that is where I'm going to use this blue part. Okay, so for the induction step, I need to see the notation. Okay, so let's say it holds for n minus 1, and then say the result say uniqueness holds for n minus 1, and A, which is in f to the m cross n, is row equivalent to B and C, both RREF. So both B and C are row reduced alpha, and let's say B is not equal to C. I think that we have to say, right? Okay, we will get to that part. So that assumption we'll get to later on. But first of all, let us now say, okay, let me chop off the last column of A, the last column of B, and the last column of C. Let's call these as A prime, B prime, C prime. Then these are fewer number of columns, right? So now step A. I'll break it down in steps. Let A prime equal A with last column deleted, and similarly B prime and C prime. First claim, if you take, remember, B and C are matrices in row reduced echelon form. First claim, take any matrix in row reduced echelon form, chop off the last column. That is still in row reduced echelon form. Why? I mean, verify. Are the zero rows above the below the non-zero rows? That still holds. Is the leftmost entry in every row non-zero row a 1? That will still happen. At most, there will be a leading one in the last column which you chop off. But then there are no entries beyond that. So it was the leftmost entry, but it was also the rightmost entry. You killed it. So there are no leftmost entries. The row becomes 0. The rest. Right? Are the entries above and below a row a leading one 0? Well, if you chop off a column, it doesn't affect the remaining columns. So yes, and so on and so forth. So yeah. So note, maybe I should just say that. Where is this? So maybe I'll just say a couple of observations. B and C are in RREF, or just equals RREF, implies B prime and C prime are also in RREF. That's what I said. Right? But there's also another point. A is rho equivalent to B and C. So from A you do some rho operations and you get to B and C. Well, if sort of do the following, cover, think about it this way. Cover your, do these rho, I don't know, I can't write it. Write down some matrices, do row operations, but we put your hand on that last column. You see that the row operations you do, the remaining part of it exactly goes through to the same part. There is no change. Row operations treat it column by column and there is no problem. So what I'm saying is if A is rho equivalent to B and C, then A prime is also rho equivalent to B prime and C prime. So these 2 points are, and this is because row operations just go column by column. Rescale some entry. Fine. It rescales one entry in one column. Swap 2 rows. Well, it swaps the two entries in each column separately. Add a scalar multiple of one row to another. Well, it adds a scalar multiple of one thing in one column to something in the same column, not something in some different column. So column by column, these operations happen. Okay. So great. So now, now I have to erase this part. The blue part, that is. I was hoping I didn't, but fine. Okay, let A prime equal this thing. Fine. So first of all, this happens. Now I think I have to say that suppose, yeah. Okay, by the way. So what does that imply? I have some matrix which is rho equivalent to two matrices in row reduced echelon form. And these matrices have a fewer number of columns. They have n-1 columns. So by the induction hypothesis, I know the uniqueness applies, so B prime equals C prime. So by induction hypothesis, first of all, you have this. Now I say part B. Okay, so now let us assume that while B prime is equal to C prime, so everything except the last columns of B and C agree. Let us assume that B and C do not equal each other. Okay, so I think that's what we have to say now. Say B not equals C. So meaning the last column is different. And there exists a U. Let's see. Do I want to say U is non-zero? No, I don't. Okay, such that AU equals 0, or B, let's say BU equals 0. Either way, any of them equals 0. If BU equals 0, then remember B comma 0. If you apply some elementary row operations, you would get to A comma what? Well, anything, as I said, any row operations applied to 0 can only give you 0. So this is 0. And similarly, if I apply elementary row operations, I can get to the row reduced echelon from C. But this column must still be 0. So BU equals 0, the set of solutions is if and only if AU equals 0. The set of solutions is if and only if CU equals 0. Right? But then if BU, so suppose there exists a vector such that this happens. Well, because BU and CU both equal 0, so B minus C times U also equals 0. But now B minus C, because of this equality, only has the last column non-zero, right? And B minus C only has last column. The last column is non-zero because we are assuming that B is not equal to C, and all other columns are equal. So the last column is non-zero. So you have something like 0, 0, 0, and then something star, 0, 0, 0, 0, star, like this. And then we have U1, U2, UN, and this is equal to 0. 0, 0, 0, star. But you see, what is this thing? This is this entry times UN, this entry times UN, this entry times UN. That's what this column is. And at least one of these entries is non-zero. So that non-zero entry times UN must be 0. So UN must be 0. So I'm going to erase this, but I will ask you to figure it out. Why this is true? Because B minus C times U is 0, this implies UN must be 0. So this is one thing. So right now I'm just saying take any vector U in R, not Rn, what is R here? Fn, sorry, my apologies. Take any vector U in Fn such that Bu equals 0, but that is if and only if AU equals 0, if and only if CU equals 0, they are all rho equivalent. And we just saw in the lemma that they have the same sets of solutions. So that means that, and this is their rho equivalent because when you augment the matrix by 0 and apply row operations, you still keep getting zeros in the augmented part. So in particular, if you have such a U, then in particular B minus C times U is 0. So the last column, and since B minus C is very, very special, this implies that UN is 0. Great. So now what do we do? So basically what we are saying is, so we just said, so any solution of AU equals 0 or BU equals 0 or C equals 0 A or B or C, right? So I can put B here or C here. Actually, let me put B or C here. Must have, as I took any solution of BU equals 0 and prove that this implies, because it also means CU equals 0 and you subtract, it implies the last coordinate is 0. Must have UN equals 0. But B and C are in row reduced echelon form. So that observation that I wrote, this thing that I just erased, implies that B and C both have a pivot 1 in their last column. By above blue part, both B and C, which are in RREF because they are both in the reduced row reduced echelon form, have a leading 1 in their last column. I am putting columns because there are two matrices here. Okay, so they have leading 1 in their last column, sorry. But where must this 1 occur? It must occur in the row just below the leading 1 in B prime and C prime, right? And this occurs so we know the column number, it is the last column. What is the row number of this entry? Even that is fixed. It must occur in the row immediately below the last non-zero row in the chopped off matrix. So chop off the matrix, there are some leading ones in the rest of it in B prime or in C prime. Look at the last row of B prime, which is non-zero. The very next one must contain the leading one, because otherwise, every zero row must be below every non-zero row. That's fine. Oops, I should erase all of this now. And similarly for C, that leading the leading 1 in the last column must occur in the row immediately below the last non-zero row in C prime. And here is the fun part. B prime and C prime are the same. That means that B and C both have a B and C, not B prime C. B prime C prime are identical. B and C just differ in the last column. But then you see, they must have a leading one in the, you know exactly which position, and it is the same position. They have a leading one in the same position in the last column. But if they do that, all other entries in that column are zero because it's a leading one, and B and C are both in row reduced echelon form. Therefore, the last columns are also the same because it's just one entry which is 1 in the same position in the last column, and every other entry is 0. So I won't say all of that, but as all other entries are 0, in the last column of B and C, are 0, we get B equals C. Because all the remaining columns were identical. Now the last column is identical. Same position leading 1, every other entry is 0. So every column is identical. So we started by assuming this doesn't hold, and we proved that it actually does. So this is a contradiction. This is a notation for contradiction, and that proves it. The assumption that B is not equal to C cannot be true, because even then we prove B equals C. Okay, so great. That's what it is. Okay, so now let's get down to the corollaries, and I don't know if I will have time in 20 minutes, but we will see. Okay, well, I will have time to prove the theorem, which is prove the fact that invertible matrices are square. I don't know if I will have time to finish the chapter. If you will, we will see. So now let me write. So this is the proof, end of the proof, that every matrix is row equivalent to a unique matrix in row reduced echelon form. Now we have to worry about, now we have to look at a few nice consequences. So as I said, this uniqueness part was slightly tricky because of this blue part. I didn't actually write down the proof of the blue part. I left it for you guys to write. Okay, so corollary 1, corollary 2. The corollary 1, they are both important statements now. Corollary 1 basically is going to tell us everything about how to solve a linear system. When is there a unique solution? When are there infinitely many solutions? And when are there no solutions? Okay. So let's do that. So corollary 1. Given the linear system, this is actually a lot of writing, not as much explaining. Right. Given Ax equals B, so given the linear system, let's say Ax equals A. And then let us write down the augmented matrix A comma A and its row reduced echelon form B comma B. Let B equals row reduced echelon form of A comma A, or A partition A. So let B be the row reduced echelon form. Okay, so here basically there are only two cases. One is when there don't exist solutions, one is when there do, and when they do, there are two further cases when there are infinitely many. So one, when you have a row reduced echelon form, so look, you have some number of, you have some rows which are non-zero with a leading 1. Maybe the scalar entry for B in that row is 0 or it's non-zero. That's perfectly fine. Okay? Either there are free variables or there aren't. If there aren't any free variables, you get x equals the scalar. Otherwise, if there are free variables, you get x plus 3y plus 4w is a scalar. So x equals scalar minus 3y minus 4w. So minus the free variables. That's fine. Those don't rule out the existence of a solution. Right? Solution always exists. The problem happens if you have 0, 0, 0, 0, 0 here and 1 here. Or not 1, but non-zero entry. Then you get 0x plus 0y plus 0w equals 1. How can 0 equals 1? The field axioms don't allow 0 equals 1. And that is precisely the problem that happens. Okay, so if there exists a zero row, sorry, what should I say? If this BB contains a row, if BB, this is not a good pen. Contains a row 0, 0, 0, partition 1, then you have a problem. Then used to be a problem. Then Ax equals A has no solutions. That is obvious, right? Why does it have no solutions? Because it is rho equivalent to Bx equals B. That's the point of rho equivalence. And this system has no solutions because you can't have 0 equals 1. 1 or any non-zero number, of course, right? So I can always, and that's the whole point. Right? If I have a 0 row here, but a non-zero number here, then I can still apply an elementary row operation to make it zeros and a 1. So regardless, when you get the row reduced echelon form, you would actually have a leading 1. And then everything else would be 0 rows. Sorry. Why is there such a loud noise? Anyway, so the point is, yeah, if the matrix was an RREF, then this entry has to be a 1 if it's non-zero, because you can rescale and make it a leading 1. Okay, so this is the first condition. Otherwise, there always exists a solution. So, and so else, all non-pivot columns. So, okay, you have these leading ones which correspond to the pivot columns, and you have the non-pivot columns. Non-pivot column, let me even mention it, i.e., not containing the leading one. Columns not containing so else all non-pivot columns correspond to free variables. And we saw examples last time already. Correspond to free variables. These are all sort of poorly functioning pens. We'll get there. Okay, free variables and take any choice of each of these variables that uniquely determines the pivot variable. And any choice of these variables, any choice or choices of these free variables uniquely determines the pivot variable. Pivot variables. So the pivot variables are not free because they are uniquely determined as x equals 3 minus 4y minus 5y. That kind of. Okay, this is not enough. So I'm going to say a little more. In particular, okay, so now there's part A and there's part B. There exists, so when can there be infinitely many solutions? Well, the non-free variables are always uniquely determined. So there's an infinite many solutions if and only there's a free variable. There exists a free variable, at least one, if and only if Ax equals A has infinitely many solutions. All of this is under the assumption of the else part. Remember, all of this is under the assumption you don't have this in your RREF. Under that assumption, Ax equals A has infinitely many solutions. Okay, part B. And when is there unique solution? Well, that's just if and only that doesn't happen. And so there is this unique, so conversely, if you will, there is a unique solution. This is the symbol for unique, exclamation mark. To, I guess, AX equals A or BX equals B. If and only if, what happens? Well, there are no free variables, which means every column of the row reduced echelon form in B must be a pivot column. Every column is a pivot column, is a pivot. How can that happen? What kind of row reduced echelon form matrices have pivots like this? I.e., think about it for 2 seconds. Let us, you can pause the video. And for those of you who just want to enjoy the show, B must be of the following form. It has to have a 1 and then no free variables. Okay, 1, 0, 0, 0, 0. The next entry must be, this is not a free variable, so it must be a 0 here. And any non-leading 1 is a free variable. Even if these are zeros, that's a free variable. So this cannot be allowed. Therefore, this must be a 1, and then this must be a 1, and so on. Okay. So for example, you can stop here. This is a RREF. There are no pivot columns. That's all. I don't care that there are these 0 rows, as long as the B also is 0. Right? So, and that's exactly what happens in general. In general, what you get is B and the matrix B because of the else part, this else part. There is no row like this. So B and B must be equal to identity of some size and then 0 matrix, so many 0 rows. And similarly here, some whatever, let's call it B1 prime. And this, of course, must be 0 because every 0 row here in the RREF cannot have a 1 here. So all of these are 0. This is what it is. This is corollary 1. So this is when you have no solutions, infinitely many solutions, and unique solutions. Everything is written in terms of the row reduced echelon form. That's where you really reduce your problem to, and that's what you read out. So once you have obtained the row reduced echelon form, then just look at the row reduced echelon form. If it contains something like this, then you are in bad shape. If it contains something like this, then it's unique. And if neither of these holds, then there are infinitely many solutions. So that is 1. Okay, so now in the rest of the thing, I will use black ink, not blue, from my fresh marker pen. Let us write this down. Okay, corollary 2. So now this is the thing about matrices being invertible. Okay, yeah. So F is any field. F a field. This time there is no restriction on the characteristic. And A belongs to F M cross N. It's a matrix. If A is invertible, then M equals N. That is the theorem we have to prove, right? Okay, great. Proof. Suppose not, say M is not equal to N. Now remember homework 2. This is where I'm actually going to use homework 2, which was very easy problem. If A is invertible, then A transpose is invertible, right? So I have both A and A transpose. One of them is, no, let's say M and N are like 3 and 5. So one matrix A is 3 cross 5. One matrix A transpose is 5 cross 3. I choose the one for which I think M is less than N, as far as I remember. Yeah. So by homework 2, which is A invertible if and only if A transpose invertible. You can replace A by A transpose if you want, but make sure that M is less than N. Without, we may assume, we may suppose M less than N. Because if A is 5 by 3, then just say, look, I have a matrix A transpose which is 3 by 5. Okay? So I work with 3 by 5, prove that 3 equals 5, and then go back to A. If A transpose is square, then A is also square. When I say prove that 3 equals 5, I mean the orders are equal. Yeah, I mean A transpose is square. But if a matrix is square, if and only if its transpose is square. So that I don't even write that. So we may suppose that M is less than N. Okay, great. Now let's write down. Suppose B equals A inverse, right? So let B equals A inverse, which is still N cross M, and C equals RREF of A, which is of course M cross M. So I have these two matrices. One is M by M, one is N by M, and I'm assuming that these are of difference. These are neither of them are square. Okay, fine. Okay, so let's see. So because C is M, so this is a row reduced echelon form matrix, and it is M cross N. M is less than N. So there is 3 by 5. So something. Each row can contain at most one leading one, obviously. There are more columns than rows. So that means there is at least one free variable. Yeah? So there is at least one free variable. Because M is less than N. And C is in RREF. So C has at least one free variable. So if I take any system involving C, then it has free variables. So by corollary 1, which is what this is why we needed to prove corollary 1 first. C has free variables or non-pivot columns. Now I'm going to take literally, I think AX equals 0 or CX equals 0, whatever. Okay, but anyway, the point is if it has free variables, then CX equals 0 has a non-zero solution. And it has infinitely many solutions. So what are solutions? Which vector satisfies CX equals 0? Clearly X equals 0 satisfies it. Anything times 0 is 0. That's homework 2, I think. Okay. But because there are non-pivot columns, there are infinitely many solutions. So there are at least 2 solutions. And one of them is the 0 solution. So there is at least a non-zero solution. As a non-zero solution, let's call it X naught. Not equals 0. Okay? So we have this. But now, if CX equals 0, then AX equals 0. By the way, because we are taking 0 to be the last column, in corollary 1, case 1 doesn't occur. Corollary 1, part 1, note. I'll say note. Corollary 1, part 1 cannot occur. Why can it not occur? Because that required 0, 0, 0, 0, partition 1. But if you start with C augmented by 0, no matter what row operations you do, you will never get a 1 beyond the partition. 0 always stays 0. There is no risk of this, which means there's at least always a solution, either one solution or infinitely many, and now we are saying there are infinitely many solutions, right? That's what it is. Cx equals 0 as a non-zero solution, x not equals 0. There is never a risk of solution not existing. Okay, but if Cx equals 0, then because C is row equivalent to A, therefore Ax equals 0. So Ax not equals 0. By the same token. And now I use my B, my matrix B. Implies B times Ax not equals 0. B equals B times 0. But B times anything times 0 is 0. What is B times Ax not? This is matrix multiplication associated. So this is BA times X naught. But BA is the identity matrix because it's an inverse. And anything times X naught is X naught. Identity times anything is itself. So identity times X naught is X naught. So X naught equals identity times X naught. Identity equals BA. So this equals BA times X naught. Multiplication is associative. So BA times X naught is B times AX naught. But AX naught is 0 because CX naught is 0. They are row equivalent. So B times 0 and B times 0 is 0. So we just said that x0 is non-zero, and over here we just derived that x0 is 0. That's a contradiction. What is it a contradiction to? Well, what was our assumption? There was no assumption here. The assumption was here. So that assumption must be false because we just got to a false statement. And therefore M equals N. And you see, I never used the characteristic of the field. I did not need it to be finite or infinite or zero or anything. I did not need the field to be finite or infinite. This is it. Okay, I think I will take 5 more minutes and finish off this chapter. It's very little to do. It's just, again, writing down more things than actually conceptual things. Here it is. So what we've just proved here, so what we've said is that non-square matrices cannot be invertible. That's what we are saying. The question then naturally becomes, which square matrices are invertible? Which square matrices are invertible? And I'm going to give you now, as I said, I will end with 4 or 5 different equivalent conditions. So I'll say that a matrix is invertible if and only if it satisfies 4 other equivalent conditions. Okay, so let's see what they are. The nice thing is each of these, the proof is very short because what I'll prove, well, let me first write this down. So theorem. So now, as I said, we already saw that non-square matrices are not invertible. So let's just start with a square matrix over an arbitrary field. Yeah, so theorem. So given, let's say, a field, a natural number, and A in F to the n cross n. I'm going to write down 4 letters here, which, if the more you see mathematics and proofs, the more you will see these letters. T, F, A, E means the following are equivalent. Meaning I'm going to write down multiple statements and each of them implies the other and is implied by the other, if and only. Okay, so the following are equivalent. Great, so 1, I think A is invertible. What does that mean? I.e., there exists a unique matrix B, which of course we will call A inverse in F to the n cross n, such that AB equals BA equals identity. Okay. Second is if A is invertible, then for all B in F to the n, AX equals B, this linear system, has a unique solution. I told you that there are possibilities when that has a unique solution, but this has a unique solution. I won't even tell you what that solution is, but now I will. This is so, I'm saying that this condition holds. AX equals B has a unique solution for every output vector B. Let me reduce it to a single output vector B, which is B equals 0. AX equals 0 has a unique solution. If that happens, then it has a unique solution for every B. So 2 is much stronger than 3, but actually not. It's actually equivalent. As long as A is square has a unique solution. What is the solution? Well, you can obviously see for yourself. X equals 0. I mean, I can tell you the solution here as well, but I won't because you will see it in the proof. The fourth, I think, is to do with the row. Yeah. Reduced echelon form of A. A is a square matrix is invertible if and only if its row reduced echelon form. Well, you know when these things have unique solutions, right? They are the identity matrix. And that happens if and only if A is a product of elementary row operation matrices. Okay, so I'm just getting to 90 minutes. But as I said, please give me 5 more minutes and then I will finish the proof and we can stop. Okay, so proofs. I might even just need this much space to finish the proof. The part below that theorem and this book. We'll see. The proof is not very long. All 5 steps. So what we are going to prove is the following. I'm going to prove that 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, and 5 implies 1. So suppose I want to prove 3 implies, suppose I want to prove 2 implies 5. Well, I say 2 implies 3 implies 4 implies 5. So that's clear. Suppose I want to say 3 implies 2. Well, then you say 3 implies 4, 4 implies 5, 5 implies 1, and 1 implies 2. So 3 implies 2. Yeah, so it's enough to prove this is the shortest number of implications you have to prove. If you can, if you're lucky enough that the proofs are short, then some kind of such cyclic implications is the shortest number you would have to prove that they are all equivalent. So let's do it. So proof. Let's start with 1 implies 2. So if A is invertible, right? So start with Ax equals B. Then I can multiply on the left by anything. Because there exists such A inverse, I can multiply by A inverse. A inverse times Ax equals A inverse times B. Right? And clearly now by associativity, I won't prove this. This is A inverse A times X, which is identity times X, which is X. This is just X. So clearly X, so if it is to be the case that Ax equals B, then X must be equal to A inverse B. So I'm not saying the solution is unique yet, but I'm saying the solution is either unique or doesn't exist. So you have to check that this is a solution as well. And indeed, A, so if X equals, so let's put a comma here, comma, and if X equals A inverse B, then Ax equals A times A inverse times B. But again, by associativity, this is equal to B. Because again, this is A inverse times B, it's identity times B, which is B. So you see, I use the fact that A inverse times A is identity, and I use the fact that A times A inverse is also the identity. So we make use of both the inverses, both sided inverse. That's why you really need a two-sided inverse there. So 1 implies 2 is easy. 2 implies 3 is even more easy. That's obvious. Because if it's true, well, set B equals 0, you get this answer. A inverse of 0 is 0. Anything times 0 is 0. 2 implies 3 is obvious. I won't even, I'll just say it's obvious. 3 implies 4. Well, if Ax equals 0 is a unique solution, well, we know what happens, right? When does it have a unique solution? By corollary 1. The row reduced echelon form of A. 1 second. Sorry, so by corollary 1, the row reduced echelon form of A has to be of what kind? It has to be something like, we said that actually. It is identity and 0. But the point is, this is a square matrix. So you cannot, this already is a square part. All the rows and all the columns are exhausted here. There are 0 number of 0 rows. And square implies the identity matrix. 4 implies 5. This is corollary 1, part 2, whatever. I won't write that. 4 implies 5. If row reduced, what does this mean? It means that A is row equivalent to the identity matrix. So from starting from A, you can do finitely many row operations, act on A, and get to the identity matrix. So we know that A is the row equivalent to identity. So identity equals, I'm going to just put something. So start with A, then I apply elementary row operations. But remember by homework, by some lecture, that is the same as applying pre-multiplying by some elementary matrices, right? So let's just call it E1. I'll just call it E1. Or let's call it matrices. Let's call it M1, M2, let's say N. Where each Mi is an elementary row matrix, hence invertible. But then what can you say about A itself? Well, A is whatever this big product is, times A is identity. So this is the inverse of it. And so, or you can take the inverse of that set. A equals Mn, M1, inverse. And I think we already saw in homework too that A times B inverse is B inverse times A inverse. All of these matrices are invertible. So you get M1 inverse, M2 inverse, Mn inverse. Okay? And now here I make use of the fact that the elementary row operations are reversible. The reverse operations are also elementary row operations. This translates to saying that the inverse of elementary matrices is also an elementary matrix. And this is a product of elementary matrices. Which is exactly what we want. A is a product of elementary matrices. Okay. And finally, 5 implies 1. But that's exactly the same as 4 implies 5 in some sense. If A equals, let's write down A equals M1 prime, M2 prime, Mn prime is a product of elementary matrices. Then each of them is invertible, so then check that A times Mn prime inverse. Okay, first of all, let's put it this way. Let's define. I'll define my matrix B. I want to prove that A is invertible. So I want to prove that there exists a B such that AB equals identity and BA equals identity. Let me give you that matrix B. Then define B equals M prime N inverse. I'm just taking the inverse of this matrix, right? That's what I have to do. M prime N minus 1 inverse, M prime 2 inverse, M prime 1 inverse. Okay? And now just multiply this by M1 and Mn and check that this is true. It is trivial to verify, easy to verify. That this happens. One easily checks that A times B is B times A is identity, and that means that A is invertible. The fact that such a matrix exists means that A is invertible and B is not. Okay, so that actually ends. Sorry, it took a little while extra, 10 minutes extra, a bunch of interruptions. Yeah. But yeah, so that ends the chapter on matrices, row operations, and so on and so forth. Row reduced echelon form. Okay, so next time we will start with vector spaces, dimension, basis, and all these things. Slowly, but yeah, we will now get to those. I should probably show you here if you want to pause the video to look at these notes. Okay, see you next time.